Hi, this is Dan Bowen, your friendly neighborhood stratospheric balloon expert. Let's continue our informal exploration of interesting balloon science papers. Minimum pressure switch. Obviously, the automatic ballast valve must not be in operation while the balloon is rising. This will be a waste of ballast. Therefore, the automatically operated needle valve is closed until the balloon reaches altitude. This is accomplished by having the loaded diaphragm of the altitude control open to the atmosphere until the balloon descends from a minimum pressure. Minimum pressure means maximum altitude. At this time, an electrical contact is made and a squib cuts the restraining cord and allows the needle valve to seal off the diaphragm from any further access to the air. And that is exactly what we learned from the diagram. The capsule then contains a volume of air which has been trapped at the existing pressure at max altitude and temperature at the time of the operation of the sealing switch. Thereafter, the aneroid, that's the diaphragm, the little can, will withdraw the ballast control needle valve when the ambient pressure increases. That means when the balloon goes down to the point where the entrapped air is compressed below its original size, just like we talked about. Figure 4 shows the minimum pressure switch, which makes the electrical contact at the time of seal-off. So that would be at the maximum altitude when that cord gets cut. This is going to show us how that little squib is triggered. Consists of a trapped volume of air that is allowed to escape to a mercury pool as long as the outside pressure is decreasing. Well, that's complicated sounding. As soon as the exterior pressure increases once more, however, the mercury is drawn into the tube, making the seal-off contact between two electrodes. That sounds pretty cool. So let's go take a look at the diagram before we try and break down that little description. So figure 4. Minimum pressure switch, mercurial. Let's see if we get any. Not very good resolution, but let's try and read these things. So we've got a stopcock, normally open to atmosphere, closed off immediately before balloon ascent. So when you're about to launch the balloon, close this valve. And that's meaning the people holding onto the thing, they need to close that valve. Then there's an air chamber, which is trapped below this valve. Then there appears to be capillary tubing, wire leads, platinum tip contacts, and mercury. Well, this is really fuzzy. At first glance, it's kind of hard to decipher this, but we have a clue from the text. So we know that the wire leads will go in here and they will not be touching each other because this whole device is an electrical switch. So they will not be touching each other until they want it to. And because there's mercury involved, we know that it's a very common old-fashioned technique to allow mercury to engulf two wires. And mercury is electrically conductive, so it's just like you had touched the wires to each other. So as the mercury approaches those wires in the tube and covers them, the electrical circuit is closed, which then brings power to the squib, which fires the charge, which cuts the cord and closes that diaphragm at maximum altitude. So how this thing is actually doing that is really not easy to see by this diagram, and we'll just go back to the text. So Here we are. Consists of a trapped volume of air. Well, that's the big pod that we saw. That is allowed to escape through a mercury pool. Sort of like it sounds like the mercury is in the U-shaped bottom of a pipe that goes down, turns around, and goes back up. Just like the water trap, the P or the U trap, they call it a P trap or a U trap, underneath a sink, where when water runs down, it actually fills the bottom half of that U bend, and to prevent air from going through and back out to the sink so you don't smell the sewers. But in this case, they are relying on the fact that the air that's trapped in there at sea level is going to want to escape as the balloon flies higher, because the air pressure outside is going to be less than in that little glass pod. And the mercury is not very strong at being able to hold back that air pressure from escaping out into the lower pressure atmosphere. So the air bubbles through the mercury and up through the other side and escapes out to the atmosphere. And it keeps doing this, bubbling as the balloon is rising, as the air pressure inside needs to escape as it gets higher than the outside air, until the balloon reaches its max altitude. And what they say here, as soon as the exterior pressure increases once more. That's very confusing reference here. What they mean is, this air is bubbling out through the mercury as the balloon is rising. And when the balloon stops climbing, the air pressure is not changing outside. So the air pressure inside doesn't need to escape. And when the balloon starts gradually sinking again, the air pressure inside is now going to be lower than it is outside, because the air inside this pod equalized at maximum altitude. And as you go down through the atmosphere, the air pressure outside increases. So air is going to want to shove back up towards the pod through the mercury. And because the tube is really small, it's going to push the mercury up a little bit as the air bubbles through it. And right above the mercury on the inside tube are the two wires. So as the mercury is shoved up the tube a little bit, the mercury engulfs those two wires, making the electrical contact, firing the squib. So basically, this all happens as the balloon sinks just a little bit. Then all this is triggered. There we go. Let's take one peek at the diagram of the whole system before we go today. So this is kind of neat. We can see here the ballast discharge tube, where it drains out from, the automatic ballast valve right down here, which is the mechanism that we studied with the diaphragm. The minimum pressure switch is here, or maybe this tall cylinder. That's what we just explored, which has the mercury in it. There's a filter and a ballast reservoir. So the kerosene filled this big reservoir, and the filter was in there probably to take out any dust and sand and hairs before the kerosene flowed through the ballast valve. And that is because the needle valve we talked about is really small. It is needle sized. And if you had a grain of sand flow through the hole when the needle was very close to being closed, it could jam in between the needle and the edge of the hole and prevent the valve from ever fully closing again, which would suck. So you put in a simple coffee filter and prevent that from happening. Then we have a battery box. Got to have power for your squib. A vent tube. Vent tube. We haven't talked about that so far. vent tube. Off the top of my head, I'm not sure what that goes to, but we'll come back to that. Oh wait, does it go all the way up here? I'm still not sure where that comes from. And we have the manual ballast valve right here. I can't remember what that was for. Maybe it was for testing? Can't remember. But anyway, that's what the whole apparatus looked like in a nice old line drawing. And of course, this vent on top is necessary so that as the kerosene drained, air could come in behind it and replace it in that reservoir. All right. That's all for today. Be sure to like this video, share it with your friends, and subscribe to the channel.